Welcome to our chemistry video on pH. Fa. No, don't call it fa. Call it pH. I mean, come on. But what even is pH? What do I mean when I say pH? Well, first, we should know what it stands for. We don't know what it stands for. The guy who created it, the Danish chemist Soren Peter Lars Sorensen, actually never told anybody why he called it pH. So it's just kind of there. But the actual thing that pH is it's a very useful way to quantify the concentration of H plus ions, or protons, in a substance, therefore determining its acidity or basicness. And so the reason we have pH is because if you just give the flat out number, it's not very user-friendly. Like, you want to know what the concentration of protons in the typical human blood is? It's 4.6 times 10 to the negative 8 moles per decimeter cubed. That's to the negative 8th. You're not going to use that number in calculations. It's just too difficult. So we came up with pH. And what is pH? Well, pH is simply the negative logarithm of the concentration of hydrogen ions. And the logarithm is obviously, it's the base log. It's 10 log. And so it's basically the negative number to which the base 10 is raised to give your concentration of hydrogen ions. So this can also be expressed as your concentration of hydrogen ions equals 10 to the power of your negative pH. That is, pretty simple. And this creates a basic scale. Typically it goes from 0 to 14 of solid whole numbers and decimals that aren't to the negative 8th. So they're just whole numbers. And it's really easy to work with that. It's a completely arbitrary scale, has no units. So it's just pH, and it's inversely related to the H+, the concentration of your hydrogen ions. If you have a really low pH, the more hydrogen ions you shall have. And so if you have a really high pH, the less hydrogen ions you will have. So low pH is associated with acids, because acids have lots of hydrogen ions, while high pH is associated with bases, because bases have very few hydrogen ions. And finally, a change of 1 pH unit, so from 1 to 2 pH, represents a tenfold change in the concentration of hydrogen atoms. So if you go from 1 to 2, you now have 10 times less hydrogen protons than you did before. And that's pretty much pH. That's the simplest it sort of gets. So pH scale, at first glance, because we're measuring concentration of hydrogen, might appear to be more suited to acids. But remember, as Kyle said in the last video, we treat our acids and bases equally here, even with pH. So on the scale, we can also determine whether your thing is basic. In fact, there's a universal number of neutralness, 7. 7 is typically the number we associate with being not acidic or basic. If you're higher than 7, then you are a basic, you are alkaline. If you are lower than 7, then you have now become acidic. So as you go down the pH scale, you become more acidic. As you go up, you become more basic. Most of the time, they're positive numbers. You can get negative numbers on the pH scale if you have a very, 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 very strong acid. Like, I'm talking stronger than sulfuric acid, stronger than battery acid here, stronger than hydrochloric acid, just super strong acid. We don't typically get those. So most of the time, your pH is going to be positive. Now, how do you measure pH? Well, you use a pH indicator. Whoa! They're typically devices. You put the little probe in the thing. It tells you what your pH is. You can also use pH, a universal indicator that will have different colors ranging for your different pHs. And that's really the main way that we measure pH. Moving on, a lot of acid-base reactions to the acid and base, involve the ionization in aqueous solution. When we have an acid or base, because they are so volatile and so dangerous, we typically dissociate them into water, creating an aqueous solution that's more diluted and therefore will not burn your face off if you accidentally get it on your face. It might just cause mild irritation. So, for example, instead of using pure hydrochloric acid, we use 0.1 molar hydrochloric acid. It's really just for safety reasons. And so, for this reason, we can write an equilibrium equation between the dissociation of water into hydrogen and hydroxide ions. So the equilibrium equation, as you might remember from equilibrium, is the concentration of the products over the concentration of the reactants. In this case, it would be the concentration of hydrogen ions over hydroxide ion times hydroxide ions over the concentration of water. Concentration of water is a liquid. Water doesn't ionize very typically, so we can just assume that the concentration of water is a constant. So now our equation, to create a modified equilibrium constant that we called K sub W, K sub W equals the hydrogen ions, the concentration of those, times the concentration of the hydroxide ions. And this is known as the ionic product constant of water, and it has a fixed value. And that fixed value is at a specified temperature. At 298 degrees Kelvin, the ionic product constant of water is 1.00 times 10 to the negative 14. And so in pure water, because the hydroxide ion concentration should equal the amount of hydrogen ions, because it's pure water, they're all going to be together, not typically dissociated. That means that the hydroxide, the amount of hydrogen or hydroxide, whatever one you want, the concentration should equal the square root of that ionic product constant of water. So at 298 degrees Kelvin, the concentration of your hydrogen ions should be 1.00 times 10 to the negative 7, which gives a pH of 7. And didn't I just say that's our universal neutral number? Guess what? Water is neutral. Bam! That's how we know that water is neutral. And so that's the pH of water at room temperature. And that's how we typically use to judge our pH scale. And using that, we can now determine that the relationship between the hydroxide and hydrogen ions, the concentrations in any given substance, is inverse. More hydrogen ions, less hydroxide ions. More hydroxide ions, less hydrogen ions. It's a pretty simple dynamic that basically creates the difference between acids and bases. Like, for instance, if you had a scale, if you just had the pH scale laid out for you from 0 to 14, and you wanted to determine your concentration of hydrogen ions or hydroxide ions in either one, and you put them both on the same graph, the line between the two of them would slope up, straight up. There would be no hydroxide at the lowest and no hydrogen at the highest, and then slowly the hydrogen would decrease as you got higher, and slowly the hydroxide would increase as you got higher. And so that perfectly typifies our inverse relationship. And therefore, if we use that equation that I just gave you, our ionic product constant of water, we can determine if you know the concentration of hydrogen ions, or if you know the concentration of hydroxide ions, the concentration of the other. You just break that equation. The concentration of hydrogen ions is going to equal the ionic product constant of water over the concentration of hydroxide, and vice versa. And so that's a really easy way. So a summary of the steps is you can go from pH, you can use your pH, and then you use 10 to the power of the negative pH to get to your concentration of hydrogen ions. And then from there, you can also use your ionic product constant of water over your concentration of hydrogen ions to get to your concentration of hydroxide ions. Going backwards, use the ionic product constant of water over your concentration of hydroxide ions to get back to your hydrogen ion concentration. And then just use the negative log, the negative 10th log of the hydrogen ion concentration to get back to pH. It's a kind of like a figure eight sort of system that we have here, and it makes it very easy to go back and forth and back and forth and back and forth. And that's really it for pH. That is what we do with it. And so pH allows us to move straight into how do we determine the strength of an acid or a base, because that depends on the extent of the ionization. Once again, we always dissolve these acids and bases in water, and once they get into water, they ionize. And so, how much do they ionize? That's what determines the strength. If the acid dissociates fully and exists entirely as ions in solution, it is a strong acid. However, if it doesn't, if, let's say, some of it stays in its full form, then it's a weak acid. So, for example, a strong acid. A very strong acid is hydrochloric acid. It's one of the strongest acids we know. And when you dissolve hydrochloric acid in water, it will dissociate fully into hydronium, or H3O plus ions, and chloride, or Cl minus ions. It will almost completely dissociate. However, let's take another example. How about let's take ethanoic acid, CH3COOH. It's a very weak acid. If you dissolved it in water, sure, you get some hydronium and you get some CH3COO minus, but some of that initial acid, that ethanoic acid, would still remain there, undissociated, in the water. And that means that it's a very weak acid. As a matter of fact, something that you can count on when you are dissolving a strong acid, you will create a weak base as a conjugate base if we're going by the Bronsted-Lowry definition. So let's say, back to that, dissolving your hydrochloric acid into water. Well, your conjugate base of hydrochloric acid is going to be chloride, which happens to be a not very strong base because, as a strong acid, hydrochloric acid really likes to give up those protons. So as a result, chloride doesn't really like to take them back. It doesn't want to become hydrochloric acid. Hydrochloric acid likes to give that crap away. And so chloride does not want to gain anymore, and therefore it is a weak base, because a weak base is going to be something that does not accept protons very easily. If you remember our Bronsted-Lowry definitions, acids are proton donors, bases are proton acceptors. So if you're really good at accepting protons, you're a really good base. Chloride is not, and hydrochloric acid is a really good acid. On the flip side, if you have a weak acid, its conjugate base will be a very strong base. So back to that example of ethanoic acid. When you dissolve it in water, the conjugate base is going to be CH3COO-, which will be a very weak base. It does not quite like to give away any more hydrogens. It probably will refuse to, as a matter of fact. And so that's basically the dynamic you have here. And once again, it's the same vice versa. Bases and acids are really like two sides of the same coin. And so, once again, if you have a strong base that you dissociate, its conjugate acid will be weak. If you have a weak base that you dissociate, its conjugate acid will be strong. And that's a pretty simple dynamic there. And so, another thing, weak acids and bases are far more common in real life than strong acids and bases. So, some common examples of strong acids and bases. Strong acids, hydrochloric acid, HCl, nitric acid, HNO3, sulfuric acid, H2SO4. Those are very strong. You're not going to find those commonly in if you just go outside and you look for acids. We have to manufacture them. Now, weak forms, ethanoic acid, CH3COOH, carbonic acids, H2CO3, phosphoric acids, H3PO4. You're going to find those pretty easily. In fact, CH3COOH, ethanoic acid, is an organic acid. All organic acids are weak acids. And guess what? They form organically, naturally, in our bodies. They're very, very, very common. On the same side, the same thing with bases. A strong base, like lithium hydroxide, sodium hydroxide, potassium hydroxide, or barium hydroxide, you're not going to find them very often. However, if you take a weak base, like ammonia, for example, ammonia is everywhere. Or ethylamine, I'm sure you don't really know what ethylamine is. It's an amine. And amines, once again, are organic compounds that form very naturally in our bodies. And so, once again, they're everywhere. So when you have weaker acids and bases, they're going to be more common. So the further you get out in the pH scale, the more extreme ends, the less common it is. I mean, take the neutral. Water, that's pretty much the most common thing we have here on Earth. So, yeah. And now, how do you distinguish between strong and weak bases? Well, obviously, you could use pH. That's pretty much the scale. Strong acids are going to be further down. Weak acids are going to be closer to neutral. But there are other ways, too. Rate of reaction. A stronger acid is going to encourage a faster rate of reaction because it's dissolved more. If you have something that's dissolved, smaller pieces, smaller surface area, if you remember from the rate of reaction section, that results in a faster rate of reaction. And thus the rate of reaction can easily be used to determine your strong or weak acid or base. And finally, electrical conductivity. If you have a fully dissociated into ions, remember, which are very good at conducting things when they are dissociated and dissolved, you'll have a very strong electrical conductor. Completely dissociated hydrochloric acid is very good at conducting electricity. Ethanoic acid, on the other hand, not so much. Weak acids are not going to conduct electricity quite as well. And those are the three main ways to differentiate between strong and weak acids and bases. And that's all. Well, I will see you next time, where Kyle talks about the horrible process of acid deposition and how it's destroying our environment.